ax squared, I'm sorry, ax to the fourth plus bx cubed plus cx squared plus dx plus e. These can get, how high can we go, folks? Infinite. Right. Oh, I've got one more comment to make about this cubic that's right behind me here. What's the domain of that thing, again? Like I asked that question on linear, quadratic, and now cubic. Domain? All real numbers. What do you think the domain of these fourth degrees are going to be? All real numbers. Is there any trouble dropping a number x in to any of these polynomials, any of these power functions? No. There's no trouble, is there? So the domain of polynomial functions in general is always all real numbers. Always goes all the way to the left and all the way to the right. Feel good? Okay. Example, let's stick with those same zeros because we're having so much fun with them. Okay. So y equals x minus 3. Let's keep that at second degree. And let's take that other one, 2x plus 1, and let's make it second degree. Same zeros, right? Same zeros. Okay. Let's expand it. If you're watching the DVD, pause the DVD, and on paper, crank it out and see if you get the same result we do here. Expanding this binomial square. Square the first, take the product of these terms, minus 3x, and double it. Square the last is plus 9. Same kind of pattern occurring on binomial square on the 2x plus 1. Square the first, 4x squared. Take the product, 2x, double it, and square the last. Okay. Now, you look at this mess. Actually, you look at the factored thing in the first place here, and you go, oh, this thing isn't going to get any bigger than 4x to the fourth, right? You see the 4x to the fourth right there, folks? When you expand this, it's going to be a 4x squared, right? And then over here, when you expand this, it's going to be an x squared. If you take that x squared times a 4x squared, you're going to end up with 4x to the fourth, your leading term. While we're at it, think about the last term you're going to get in this string now. Remember, here's the string that we're going to get, a thing looking like this. And this last thing is a constant, e. So what's going to happen? Look at the factored form here. What's the number you're going to get for that constant on the tail end after you do the expansion? Positive 9 here times a 1 is positive 9. Right? Everybody see it? Okay. So you can see the first term and you can see the last term in the expansion. First term and the last term in the expansion if you're careful and look at the factored form if you're careful. All right, so here we go. Pause the DVD if you need to. Do the descending multiplication in your head in the arithmetic. And so here we go. Fourth degree term combo. The only one is going to be 4x to the fourth. Now I'm looking for any cubics. Minus 24x cubed. Oh, look at here. Plus 4x cubed. That's minus 20x cubed. Now look for any quadratic pairings. Here's 36x squared, and here's a minus 24x squared. Take 24 away from 36, and you get 12. No? Oh, wow. Thank you. I'm glad we're collectively doing this. Okay, 36x squared.
It's 13.
And minus 24, 36 minus 24 is 12. Okay, so 12x squared and plus 1, 13. X squared, right?
Yes.
Oh, I'm glad we're doing this together. Did I get that right when I did it? No. Thank you. Oh, yeah, maybe I did. Nope, I missed it. Okay. And then any linear terms?
That's 36.
36x.
Minus 6x.
36x minus 6x plus 30x. Is that right? Okay, so here's the expanded form of that polynomial. Do you see the general character, folks, here? Look at this leading term. It looks like an x to the fourth, which we're familiar with. Looks like what?
Is that the W one?
Up left, up right, right? And very U-shaped, right? Nice and smooth, though. Smooth, but very U-shaped, right? And stretched by a factor of 4, so tall and skinny. In other words, up left, up right. So we're going to see, sorry it's so messy up here, but we're going to see up left behavior, and we're also going to see up right behavior. Do you see the connections between what we're doing here and what we did earlier with the cubic and even the quadratic? See the patterning? Okay. So we only have 2 zeros, don't we? How about a Y-intercept? We talked about that a little while ago. F of 0 disappears, disappeared, disappeared, disappears. 9. 0, 9. Label it. Okay. So graph has to be up here to the left. Comes down to this 0, and what happens?
It bounces.
Boing, boing, right? Bounces off. So it comes down here, bounces off here at this 0 because of the even power on the factor. Comes up through 0, 9. I don't know where it's going. Might go way up. But then what has to happen? Has to come back down, and at 3, here goes Tigger again. Boing. I'll write that up here. Boing. Right? And back up. There it goes. Kind of reminds you of a W. Domain, still all real numbers. All real numbers, left and right. Question?
Is expanding the equation merely to work on our algebra skills, because the condensed version tells you everything you need to know? It tells you that you want to bounce, and it tells you if you square both end terms and multiply those together where your y will be.
Yep. Oftentimes the thing's going to come at you this way. And then what?
Factor.
Choking me up. Okay. You got to take this. It's funny, huh? Right? Okay. You got to take this crazy thing and get it back to this form to be able to see those zeros. Now, oftentimes in the real world, you can't factor these crazy things. So what do you then do? You grab your technology and utilize it as a tool to help you with it. You grab your calculator.
Do those always have symmetry?
No, there's no necessary symmetry here. Maybe it's doing this.
So you can't find the maximum by dividing, by taking the points and
No.
finding this half distance?
No. As a matter of fact, folks, first of all, where are the how many turning points?
3.
Changing from decreasing to increasing, changing from increasing to decreasing, and then vice versa again there. 3 turning points. Do you see a pattern? This 4th degree polynomial has a maximum of 3 turning points. The cubic had a maximum of 2 turning points. The quadratic, think about your quadratics.
Only has one.
1 turning point, okay? And no turning points on a linear one. This isn't so hard, is it? Okay. When I'm doing them for you. Okay. All right. So we've learned a whole lot about these things. Now, where you are going, you're all studying algebra real hard. Where you are going with this stuff, if you move beyond this algebra course, is into rates of change kind of stuff, which moves you into calculus, whether it be, as I've said numerous times, business applications or science applications, either in the life science or physical science area or engineering, physics, that kind of stuff. Wide application to this stuff. And so what you're interested in are these turning point locations, and what you know, we talked about it in other class sessions, is the slope on the graph. If you lay a ruler, a straight edge against the curve, these are nice smooth curves too, all of them, aren't they? Smooth, nice smooth continuous curves, okay? If you lay a straight edge against them at the turning points, you see what kind of slopes? Zero slopes. And you learn how to do that when you start taking calculus. You learn how to find those locations, and also, here's something kind of interesting. I'll just mention it briefly now. When you go past this maximum and you transition over here to this minimum, isn't there a spot somewhere between here and here where this thing is as steep as it's going to get negatively? A maximum negative slope in there? Yeah. And that's called something, it's where the curve inflects. It changes from concave down to concave up. And that occurs at a special spot called an inflection point. Okay? So just the introduction to the vocabulary, you'll hear that later on, not in this course, but in other courses. Okay? And you'll learn about how to find those locations. So that pretty much covers the fundamentals of polynomials and how you investigate them. And if you're asked for the end behavior, it's going to be up left, up right on this one. And it's got a couple of zeros. How many zeros could a 4th degree polynomial have?
4.
Yeah, imagine that we took this graph, and what if instead of a 9 here, I just lowered this graph down? I just grab the same equation and I just subtract off something off of here. Bring it down a little bit. Wouldn't it have potentially 4 zeros? So a 4th degree polynomial could have up to 4 zeros. How few could it have?
None.
What if I raise this graph up a little bit? Never hits the x-axis. What if I took a parabola and lifted it up so it doesn't hit the x-axis, right? Okay. Maybe no zeros. Okay, let's back up here, come back over with the camera to this other board with the cubic, the 3rd degree polynomial. We call those things cubics, a cubic. On a 3rd degree polynomial, this particular one had 2 zeros. What if I lowered that graph down a little bit? How many would it have?
3.
Potentially 3 zeros. Okay, could have up to 3 zeros. How few could a cubic have?
4.
A minimum of, always has to have at least 1, right? Think about a straight line. Isn't that an odd-powered polynomial? Linear function? mx plus b? Yeah. As long as it's got a slope that's not 0, as long as it has some slope that's not 0, then it's going to have for sure at least 1 0. Okay. So up to the degree of the polynomial, it can have that many zeros. Odd-powered polynomials have at least 1. 1 0. So sorry for the messy board work here. Okay.
So what about the bouncing thing? Because that goes away if it gets 4 zeros, then the bouncing thing goes away. If it doesn't bounce anymore, it crosses through now.
Oh, let me come back over to this board again. Let's see. If I do this, that's all a 4th degree could do, isn't it?
Well, if it comes down below the x-axis, then it's going to cross the
Yeah.
x-axis 4 times. So then it doesn't bounce off the x-axis.
Right, yeah. So that one would not have, that one would always cuts through on the factors. You want to see an example of that equation?
Sure.
Let's say this is at -5. Let's say this is at -2. And this one over here is at 3. And that one's over there at 7. An equation that would show you a graph probably very similar to this then. See if you could write it, folks. Whoops, running out of space.
That'd be x
Plus
5,
5.
x plus 2, x minus 3, x minus 7.
There you go. You pop that in your calculator and you'll get a graph something like this. It's that easy. Okay?
See that one again?
It may not dip like I've shown this low. This point may be up in here. This one might be lower. I don't know. But it's got the same kind of characteristics as that.
And so the reason,
Yeah.
or how we can know that it goes through the zeros is because all the factors
Because
are
there's no
how-
square.
how-
Very good, Diana. Every factor here has an odd power. Isn't that neat? Okay. So that, in a nutshell, covers most of the features of these polynomials, and you should be in fairly good shape. I've got about 10 minutes or so left. What I'd like to do is to come back to quadratics, because the quadratic formula I did not take time to go over with in class, and that's an intermediate algebra skill, and there's some insight there that I think is important for you here. So let's take some time to go through that. And while I'm getting ready to do that with you, let me comment. What if I had a string of data? A string of data for modeling purposes. Like the title of today's session is Polynomial Functions and Data Modeling. Okay? If I had a string of data, shouldn't you be able to build a scatter diagram like we did in the last couple of class sessions? You input the data into two lists, you generate your scatter diagram with the appropriate viewing window, and then if it looks like it's behaving like these things, you can select the correct equation modeling to do, calculation to do on it. You can do cubic regression, you could do quadratic, you could do quartic, 4th degree. Okay, and it'll fairly closely fit your data set. Okay, I'll probably not have time today to do another example like that with you, but maybe next class session we'll try to do another data problem. So I'm going to go kind of quickly in the interest of time, but all the details will be here. I provided you a handout the other day of completing the square on a quadratic function with numbers. What I want to do right now is go through this with you using the letters A, B, and C. So there's several ways I could do it. One way, what I'd like to do today is divide both sides by A. And so I'm going to write this as y over A equals x squared plus b over A times x plus c over A. I'm now going to take leave a little space after the linear term, and c over A stays on the outside there. I'm now going to take half of b over A, which is positive b over 2a. I'm going to circle it and put it right underneath here like I've illustrated previously in other problems. I'm going to square this and tuck it in right here. B squared over 4a squared. I can't just go tossing this kind of thing into an equation though, can I? Otherwise I've changed the equation. I've added this much to the equation. So on the tail end, I'm going to subtract it off. Okay, now our y over a is now equal to this trinomial up front is really a binomial square. X, and this little thing I circled goes right in there, b over 2a plus b over 2a quantity squared, are these first three terms collapsed into a binomial square. Boom. I need a common denominator to get these terms together, and you can see that I need another 4a, don't I, top and bottom here, to make a common denominator. So if I tuck in a 4a as a multiplier, top and bottom, in there, I have then plus 4ac minus b squared over 4a squared. If I now multiply the a back across to both sides of the equation, I just have y here now equals a times x plus b over 2a quantity squared plus, now don't forget I'm multiplying by a. If I multiply this expression over here times a, that a multiplier reduces with one of these down below, and I end up with 4ac minus b squared over just 4a. This fits the structure that I've shown you previously. This fits the algebraic structure, a times the quantity x minus h quantity squared plus k. So the vertex of the parabola is going to be, you know, at hk, and h, be careful, look at this. H is really negative b over 2a. Do you see that in the algebra here? The h is really a negative of b over 2a, because this is really a minus b over 2a. And the k value, the vertical shift up or down on the parabola, is this expression 4ac minus b squared over 4a. This is also minus b over 2a comma f at minus b over 2a. If you put the minus b over 2a into the original function as the input, that number, you will calculate this value, which is your k. All right, got a little bit of time left. Look at this algebra right here, this expression, this equation. Look back at the original. What's the quadratic formula, folks? The quadratic formula, how many of you don't remember it? Everybody remembers it. That's good. But what is it? It is, if you let y equal 0 here, it's the solution to this equation if y equals 0. Okay, so the solution to ax squared plus bx plus c equals 0 is your quadratic formula, which you told me you have memorized. Okay, now watch this. If I come down here in this form right here where the square has been completed, and I let the y equal 0 right here, folks, watch this. If I let y equal to 0, I have a times x plus b over 2a quantity squared plus this, now, is equal to 0. So in the interest of time, I'm just going to imagine that this thing right here is equal to 0. And so then I'm going to have this binomial square expression, and I'm going to move this term to the other side, folks. If I move this to the other side, it changes the sign of it, doesn't it? So it becomes a positive b squared minus 4ac all over 4a. if I multiply both sides by 1 over a to get rid of this a here, then I've isolated this binomial. I've isolated the binomial square, and on the right I get b squared minus 4ac over 4a squared. Messy, but not too tough. Next step is square root both sides to release the unknown in here, and make sure you put plus or minus on this mess on the right, on the radical. So we get, and I move the minus b over 2a to the other side in the interest of time and space. And the right side becomes a square root, plus or minus the square root of b squared minus 4ac, and the square root of 4a squared, you know, is 2a. And what I want to point out to you, here's your quadratic formula, that the 2a is a common denominator, is the way you usually write it. But what I want to show you is that this exhibits numerical symmetry. Numerical symmetry. So that, we've got about, what, I have about a minute left, folks? Okay, good. I always got to look back in the control room and see if they're going to cut me off or not. Okay, so I wanted to leave this guy down here on the bottom for a second. Is it, in the interest of time, this spot right here is at x equals your minus b over 2a, and the y reading right here is the f at that minus b over 2a value. That's the height right there. Got it? And if you add that radical over 2a, or subtract that radical over 2a, it takes you from this x location symmetrically to the right and left to locate those two zeros. So as I said earlier, is the solution to this equation is your quadratic formula down here, which is then going to exhibit itself as this location and this location on your parabola's graph. Okay. If you want to earn 10 more bonus points in this course, I'd like you to come in to the Resource Center, and I'll hand you a sheet of paper and put you in the testing room, a blank sheet of paper, and I'll have you start with y equals ax squared plus bx plus c, and I want you to go through this process on paper, and then give me that paper and you can earn 10 bonus points.
When do you want this by?
Oh, in the next couple weeks. Okay. So I think that wraps it up for today. What we'll do next session is we'll start out with a data modeling problem on a polynomial, and then we'll move on to where we mix some polynomials together, creating a ratio of polynomials called rational functions. That's it for today.